Atomic structure and periodicity is our next unit, and we're going to talk a little bit about the history of atomic atomic theory and the models that we are currently using, and then we'll go into electron configuration and then periodicity or periodic trends. So this first lesson is going to be on basically the waves and electromagnetic radiation and some of the history of how we discovered that. And then lesson 2 will pick up with electron configuration. So let's get started. Electromagnetic radiation was first discovered or talked about in 1800s when they kind of discovered the infrared radiation, something other than visible light. And then in 1864, James Maxwell came up with a mathematical theory to describe all forms of magnetic radiation in terms of oscillating or wave-like electric or magnetic fields in space. So that was when people first started looking at this and deciding what was going on in the world around us. Of course, it's defined as radiant energy that exhibits wave-like behavior as it travels through space at the speed of light in a vacuum. The two characteristics that we can use to describe it is wavelength, which is the distance between two consecutive peaks or troughs in a wave. So here we have, showing you right here and here, that would be a longer wavelength or a shorter wavelength. And then, of course, frequency is the number of waves per second that pass at a given point. And then we usually will measure wavelength in meters. Is the accepted value, although oftentimes we will use nanometers. So you have to remember that to do those conversions. And just to refresh your memory, 1 times 10 to the 9 nanometers is equal to 1 meter. Frequency is in cycles per second, either second to the -1 or hertz. They're the same thing. And I see that this did not get subscripted, so make sure it is in your notes. 3 times 10 to the 8th meters per second is the speed of light. And then, of course, this is the equation. That equation is on your formula chart for AP, so that means you will be expected to know how to do those calculations. And so we'll do a practice one here in a second. Recall from either Chem 1 or if you're in physics that all electromagnetic radiation travels at the speed of light and that wavelength and frequency are inversely proportional. Speaking of frequency in physics, I think it's often done with the F. I don't know why physics does it with an F, and we do it with the nu, which is a Greek letter, but it means the same thing. But they are inversely proportional, so when one is large, the other one is small. If one goes up, the other one has to go down. Okay, here is the electromagnetic spectrum. You should be familiar with it in terms of where's the high energy, where's the low energy. Energy and frequency are directly related. High frequency means high energy, but then it means a lower wavelength. So this little section of visible light that fits in between infrared and ultraviolet, that's what we can see with our own eyes. And if you'll notice, the red over here is 7 times 10 to the -7, and that's going to be in meters. Oops, I forgot to say I was going to write. Sorry about that. This is going to be in meters. And then, of course, down here is in meters as well. And then in the sky, it appears red at the top, right? And we know red, Roy G. Biv is the way that we remember the order. Red is first, orange, yellow, etc. Okay, but you do need to know the general thing. But some of this is common sense, right? I do not. Looking down here, here's my radio waves, and TV waves would fit in there as well. They're very low energy. Microwaves would be next. I don't cook my food with the television, so obviously microwaves are going to be higher energy. And then you've got infrared and visible light, and right after visible light is ultraviolet, which is what gives you a sunburn. And then, of course, you've got X-rays, which can see your bones, and gamma rays are the highest energy, highest frequency, and the most detrimental to human tissue. And they made the Hulk. Ha! So here is an example of our speed of light equation. So we're going to use C is equal to wavelength times frequency, and it's basically asking us to calculate the frequency excuse me, of red light that has a wavelength of 6.5 times 10 to the second nanometers, which is 650, right? And so we're going to use this equation and rearrange it to solve for frequency. So it's going to be C over wavelength. But before we do that, I'm going to convert that into meters because my speed of light is meters per second, so my wavelength needs to be in meters. So 1 times 10 to the 9 nanometers is equal to 1 meter, so that's going to be 6.50 times 10 to the negative 7 meters. So I'm going to plug that in over here, 3.00 times 10 to the 8th, meters, and that's going to be over 6.50 times 10 to the negative 7 meters. That was meters per second, so meters, meters. So we're going to be second to the minus 1, or hertz. And I need 3 significant figures, so it should be 4.61 times 10 to the 14 hertz. Okay? So that's how you do the speed of light equation. That's going to take us to the nature of matter. Sorry about the visual quality of that picture. Max Planck, or Planck, however you want to say it. I always think this is very interesting. At the end of the 19th century, physicists were pretty much thought they had explained everything that needed to be explained, and students were actually discouraged from pursuing it in a career because all the problems had been solved, which of course was not true. And then it was they started questioning the things that were known for at the time, and in the early 1900s it was believed that matter and energy were very different. Matter was composed of particles and energy was composed of waves. In 1901, Max Planck found that when solids were heated strongly, they absorbed and emitted energy. Think of when they were making iron tools and they put the iron in the fire, it would glow red. So that is an example of that. This ultraviolet catastrophe, defined as the fact that a glowing object did not emit UV light as predicted. So Max Planck, solved the problem. He made an incredible assumption that there was a minimal amount of energy that could be gained or lost by an atom, and all the energy gained or lost had to be some sort of integer of a multiple, as opposed to just any random number. And so he came up with this equation of delta E is equal to N, and then HV, V being frequency, and then of course we'll see that H is Planck's constant, which is 6.626 times 10 to the negative 34, joules per second. And this is the lowest frequency that can absorb or emit an atom, and the minimum energy change, which we call a quantum of energy. And we think of that, sometimes we say it's a little packet of energy. There is no such thing as transfer of energy in fractions, only a quanta in whole numbers. He was able to calculate a spectrum for the glowing body that produced this experimental spectrum. And then his hypothesis applies to all phenomena on the atomic and molecular scale. That's a lot of words to just say, hey, it's a certain amount. So here's an example using that equation. We have the blue color in fireworks is often achieved by heating copper chloride to about 1200 degrees Celsius. It emits a blue light at 450 nanometers. What is the increment of energy or quantum that is emitted by 450 nanometers? So there's two things we can do here. We have the speed of light equation, which we just used a while ago. And so we have C is equal to frequency times wavelength. And then I also know that I have this particular equation. So if I rearrange this, I get C over wavelength. So now I'm going to take that and I'm going to substitute it in for there, and I'm going to solve this all at one time. Because I'm just substituting in what I would do, C over wavelength. So now I can just do it all at one time. So energy is going to be equal to 6.626 times 10 to the negative 34 joules a second, times speed of light, 3 times 10 to the 8th meters per second, divided by 450. I'm going to convert that to nanometers real quick. I mean, from nanometers to meters. So 4.5 times 10 to the negative 7 meters. So now meters cancel out, seconds cancel out, and I get a final answer of 4.42 times 10 to the negative 19 joules. And that would be my answer to that. Photoelectric effect. Albert Einstein is credited with the discovering or first talking about this in 1900. He was working as a clerk, and he had extra time to work on physics because, you know, that's what clerks usually do. And he proposed that electromagnetic radiation itself was quantized. He was a great fan of Max Planck, and he proposed that electromagnetic radiation could be viewed as a stream of particles that he called photons. Basically, what the photoelectric effect is that light bombards the surface of a metal at the right frequency, and electrons are ejected. A minimum frequency must be met. That was whenever I copied that over, it just didn't do that symbol. Once the minimum amount of frequency is met, the intensity increases the rate of ejection. And of course, a photon is a massless particle of light. Again, sorry about the leaving, when it converted over, it didn't take the symbols with it. Of course, this is what I just showed you right here, right? And the way they got that was, again, normally it was E, HV, and C, wavelength frequency. And if I just rearrange frequency, I'm getting that, and then that gets plugged in. Okay? But you know, Einstein, he's most famous for E equals mc squared. And so he decided, or because of this, we realized that energy has mass, and so you can rearrange that equation to look like this, which I believe it's gotten shifted over in my notes. I think it's okay in yours. So does a photon have mass? Yes, it actually does. In 1922, an American physicist, finally an American in the mix, Arthur Compton, performed experiments involving collisions of X-rays and electrons. And he showed that photons do exhibit the apparent mass calculated from above. So, summary of all this is energy is quantized. It can only occur in discrete packets or discrete units called quanta, and that electromagnetic radiation exhibits both wave and particle-like properties. This phenomenon we call the dual nature of light. Sometimes it's called wave-particle duality of light, but basically it's saying that light can behave like a particle, but it can also behave like a wave. Typically, particle behavior when it is interacting with matter, directly with matter, and wave-like when it's traveling through space, typically. Okay. Here we have another equation. Since light was thought to be wavelength, now has, we know that it has some particulate behavior. Is the converse also true? So Louis de Broglie, he substituted velocity for speed of any object not traveling at the speed of light, and then you rearrange and solve for lambda, and this is called de Broglie's equation. De Broglie's equation is used to find the wavelength of a particle. So here we have some mass involved. So we're going to do that here in this exercise. We're going to compare the mass, wavelength of an electron, gives you the mass traveling at this particular speed, with that of a ball, which is much heavier and traveling much slower. So we're going to do those comparisons. So we're going to use wavelength A. Actually, let's call that wavelength E for electron, right? And we're going to substitute H is our frequency. So 6.626 times 10 to the negative 34 joules times second over the mass, which is very, very light. And then 1 times 10 to the 7 meters per second. That looks like a negative. Sorry, my pen it's just a 7. And then we get that calculation, and we get 7.27 times 10 to the negative 11 meters. And then I do the wavelength of the ball. Its mass, 0.10 kilograms, and 35 meters per second. And we get that wavelength to be 1.9 times 10 to the negative 34 meters, which is a really, really small wavelength. It wouldn't even look like a wavelength that's so small to the naked eye. Okay. That brings us to the hydrogen line emission spectrum and Niels Bohr. We're almost done with this lesson. I know this part is a little bit on the boring side unless you really like physics, so we're just trying to get through it as fast as we can. You can go back and read all this, of course, and study on or read it in the chapter if you find it more interesting. So de Broglie's equation is used to find the wavelength of the particle. It's determined that matter behaves as though it was moving in a wave. This is important in really small objects, such as electrons, but is negligible, like we just saw in baseballs. Heavy objects have very short wavelengths. When radiation is separated into its wavelength components, a spectrum is produced, and then a prism is used to separate those components. White light, of course, is a continuous spectrum. That's where we get the rainbow, Roy G. Biv. Some emitters of light radiate only certain colors and wavelength. This produces a bright line spectrum that is unique to each element. When various gases at low pressures are put into tubes, they glow in various colors. We pass that through the prism, and the series of lines is produced, and this helps to identify the element. Niels Bohr found that these absorption and emissions by hydrogen correspond to certain energy changes of the electrons. He proposed that the electron in hydrogen travels only at certain allowed orbitals, and he calculated these energy differences between the orbits and predicted the wavelengths. Worked great, but only for hydrogen. So it doesn't work for what we call polyelectronic atoms, which are basically atoms that have more than one electron, which is everything else but hydrogen. This is going to bring us to Coulombs Law. You will see a lot of this in AP Chem. When we're explaining trends and behavior of bonds, we're going to refer back to Coulombs Law a lot. So this is our first introduction to it. Unless you're in physics, you were introduced to it that way. It states that the force between two charged particles is inversely proportional to the square of the distance between them. So if you have same sign, the force is repulsive, and if you have opposite sign, the force is attractive. Like charges repel, opposite charges attract. We're going to see it again in a little bit when we talk about periodicity in the next couple of lessons. But this is a good point at any to show you that we're going to be using this. Okay, further away, in this case, further away the electron is from the nucleus, it's going to affect the charge. So, moving on, Bohr adapted Rutherford's model, sometimes called the solar system model, and suggested that electrons could only travel in a fixed orbit or shell. Here's an example of a Bohr model. Using a device called a spectroscope, it was found that these gaseous elements emitted electromagnetic radiation when heated, and that light was emitted that it had discrete packets of energy called quanta, and each element emitted a unique pattern of radiation. Here's some examples of hydrogen, neon, and beryllium. We discovered that when basically what's happening is a atom is absorbing some energy. It takes the electron and it jumps up to a higher energy level, which is called, the ground state is where it is to begin with, jumps up to the excited state, and of course what goes up must come down, and so the energy released when the excited electron falls back down to the ground state is the amount of energy, and it relates to the color of wavelength of the light. Because they're in fixed positions, they have a fixed wavelength or fixed energy when they are jumping between these two energy levels. Okay? Of course, if it's a higher energy wavelength, that means that it jumped to a higher energy level. And then when it was falling back down, it released that said amount of energy. Okay? Sometimes an electron can gain enough energy to completely overcome from the nucleus, and it may be ejected from the atom altogether. The energy required to achieve this is different for each electron, and it's what we call the ionization energy, which we will be talking about in subsequent lessons. Here's a picture of a photon absorbing energy. Electron jumps up and falls back down. So low state is energy level, ground state is lowest energy level, excited state is higher energy level. And then that's where we're going to stop. We'll pick up with that for the next lesson.